continuation to my previous class, today I will deal with the nonlinear programming problem with the inequality constraint. But before to describe about the inequality constraints, I will say few things, few properties with the nonlinear programming problem with equality constraints. Now, we know that if we consider an unconstrained optimization problem, minimization of f(x), we know the necessary condition for this would be gradient of f(x) at the optimal point must be is equal to 0. Now, this is for the unconstrained optimization, but if we consider the equality constraint optimization problem, we need to find out the Lagrangian function. I explained you in the last class in the Lagrangian function by considering the Lagrangian parameter. If we just go for the necessary condition, then this is the necessary condition, grad f plus Lagrangian multiplier lambda into grad of h x star equal to 0. Now, if we consider the inequality constraint instead of the equality constraint, that minimization of f(x), gx less than is equal to 0, where here also the same, the decision vector x is in the n dimensional space. Now, what should be the necessary condition for that? Now, we have to find it out. Not only that, if we have the constraints which are of the mixed type, that we have the equality constraints as well as the inequality constraints, that also we need to do what would be the necessary condition for this problem. Now, in continuation to my previous class where I dealt with the equality constraint optimization problem, now we are here to find out what will happen when we will have the m number of inequality constraints. Now, as you have done in linear programming, whenever you are having any inequality constraint, then either you introduce the slack variable or you introduce the surplus variable depending on whether the inequality sign is less than equal to or greater than equal to. Now, if the constraint is of less than equal to type, you introduce the slack variable. That is why here we are introducing a non-negative slack variable, that is Sj. Since we are considering the slack variable as non-negative, that is why we are considering Sj square. That is why we can make this problem as a equality type constraint. That is why you might be understanding that you must be guessing that we can handle this problem just like our previous case, where we dealt up with the equality type constraint and a nonlinear objective function. We can do the same thing, is it not? We can construct the Lagrange function, we can introduce the Lagrange multiplier, etc. Now, in that line, there is a well-known method that is called the Kuhn-Tucker condition, Karush-Kuhn-Tucker condition. In short, we are calling it as a KKT condition. There, we are extending the Lagrange theorem in the inequality type constraints. Now, that is why we will construct the Lagrange function as well, but instead of introducing the Lagrange multiplier, here we will introduce the KKT multiplier. And the significance of KKT multiplier, how to handle the problem with inequality constraint where the slack variables are there, all these things I will discuss. I will start discussing today only. Now, let me revisit about the Lagrange theorem. Now, in the Lagrange theorem we know if we consider a two variable function which is objective as well as constraint, we are considering minimization of f(x1, x2) subject to g x1, x2 is equal to b. Here the functions f and g, only one constraint I have considered, and these are of non-linear type and b is a constant. Then we can make this one as minimization of f x1 x2 subject to h x1 x2 is equal to g minus b is equal to 0. There is no harm to do it, because just subtracting b from both sides we can get it. That is why if we formulate a Lagrange function lambda L in this way, we can say that at the minimum point that should be the necessary condition, that grad of f plus lambda into grad of h at x star, where x star is the minimizer of the optimization problem. This is equal to 0. Not only that, we have to introduce information about h as well. That is why h x star must be is equal to 0. That has to be included. Now, there are few properties. What are the properties? Once we are declaring that grad of f x star is equal to, just if I just write down the conditions once more, then we can say that grad of f x star must be plus lambda of grad of h x star is equal to 0. Now, lambda is a constant. Can we not say from here that this is the vector, this is the vector, these two vectors are parallel? Depending on the sign of lambda, we can say whether these parallel vectors are directed in the same side or these are directed in the opposite side, in the reverse direction. Okay? That part is clear. Now, from the Lagrange condition, whatever condition we are getting, that is the first order necessary condition. We do not know whether this condition is at all a sufficient condition or not. Now, another point is that we are calling it x star as a minimizer of the nonlinear programming problem. Now, this minimizer is being named as the regular point. Okay? Now, what is the meaning of the regular point? We know the meaning of the feasible point. Feasible point is the point which is in the feasible space. That means the point which satisfies all the constraint set. Here also something related to that the x star is a regular point if it is in the feasible space, but it has certain other properties as well. I will discuss in the next what is the regular point. Now, as I said that a gradient of objective function is the parallel to gradient of constraint. But if we have more than one constraint, then what we do? We write down grad of f x star plus lambda 1 grad of h x star h 1, because if I consider more than one constraints together, lambda 2 grad of h 2 x star up to, if there are m constraints, lambda m grad of h m x star is equal to 0. That is why can we not say that gradient of objective function can be written as the linear combination of the gradient of constraints. Therefore, we need to understand what is the meaning of it, what is the meaning graphically. Once we have the individual single constraint, we can say both are parallel. Okay? But if we have more number of constraints, what is the meaning that the gradient of function is the linear combination of the gradient of constraints? All this meaning we need to understand one by one. For explaining those things, I am considering few examples one after another, and there are few issues also that whenever we are considering the nonlinear programming problem, even it is true for the linear programming problem, you must have been realized in linear programming problem that we are getting the feasible optimal point, but all the constraints are not active at the optimal stage. That is sure, few constraints are active, few constraints are inactive. Here also, can we just say, we say that we can get the optimal solution, but is it possible for us through this Lagrange process, which constraints are active and which constraints are inactive. And if the constraints are inactive, then the question comes, why should we include all those constraints in the set? Because unnecessary, it is giving us more labor for computation. That is why all these issues to be addressed one by one. Let me start to explain to you all these issues one by one with few examples. Let me consider the first example. Extremize x1 plus y, x1 square plus y square, x square plus y square subject to x square plus 2y square minus 1 equal to 0. What you could see that objective function is a circle and constraint is an ellipse. Okay. Let us try to see that what could be the solution for this problem. Now, this is the x and y space. Now, if we just consider the ellipse, drawing is not good enough, but this is the ellipse. Now, from the equation we can say that this point is 1 0, this point is minus 1 0, and in the y, since 2y square is equal to 1, that is why it is 0, 1 by root 2, and this is 0, 0 minus 1 by root 2, this point. Alright. Now, this is the constraint set. Only the constraint we can work through the boundary of the ellipse, because the constraint is of equality type. Feasible space is only the boundary of the ellipse. Now, if we consider that there is one circle x square plus y square, that is why it is centered at 0. Now, circle is moving further. Alright. Now, what should be the minimum value of the radius of the circle when it touches first the feasible space? Certainly, this is the point. That is why that could be one optimal point and this could be one optimal point. We have to find out these 2 points are minimum point. That is why in doing all the calculations, what we do, we let us formulate. We want to get all these things, the maximum points and the minimum points together by mathematically. That is why let us introduce the Lagrange function x y lambda. This is equal to x square plus y square plus lambda into x square plus 2y square minus 1 equal to 0, alright, not 0, this is equal to. Now, what is the first order necessary condition? The first order necessary condition should be grad of L with respect to x must be is equal to 0, which implies that 2x plus 2 lambda y must be is equal to, 2x plus 2 lambda x must be is equal to 0, and this is another first order necessary condition with respect to y. Partially differentiate, if we do the L partially differentiation with respect to y, then from here we are getting 2y plus 4 lambda y equal to 0. What else we are getting? We are getting L lambda must be is equal to 0. It means that x square plus 2y square minus 1 is equal to 0. Then what exactly we are getting? We are getting 3 equations and 3 unknowns from here. If we just do the calculations for this one, let me write down once more the equations for you. That is 2x plus 2 lambda x is equal to 0 implies 2x 1 plus lambda is equal to 0. The next 2y plus 4 lambda y is equal to 0. This implies y 2 1 plus 2 lambda is equal to 0. What else we have? X square plus 2y square minus 1 is equal to 0. Look at the first, this one. Either x can be 0 or x cannot be 0. If x is equal to 0, then what we get? If x equal to 0, then we get lambda is equal to minus 1. And from here what we get? Y is equal to plus minus 1 by root 2 from equation 3. This is one set, alright. But if x naught is equal to 0, then what you will get? This f x equal to 0, then lambda cannot be is equal to minus 1. Then what should be the value for lambda then? If x equal to 0, from here we are getting the value for y is equal to plus minus 1 by root 2, and from here we are getting the value for lambda as minus half. Okay, lambda is equal to minus half. This we are getting if we just considering 1, 2 and 3, then from 2 and 3, from 2 and 3 we get these conditions. Okay. And if x naught is equal to 0, then 1 plus lambda must be is equal to 0. That is why we are getting lambda is equal to minus 1, and from here if lambda is equal to minus 1, then we are getting that y is equal to 0 here. If y is equal to 0, then x would be is equal to plus minus 1. Okay, that is the condition. Now, from here how many points we are getting? We are getting 4 points. What are the points? These are the possible extreme points. The points are 0, 1 by root 2, because from here 0, minus 1 by root 2, that is 1, 0, because x plus minus 1, and minus 1, 0. We are getting 4. Now, what are the corresponding objective functions here? If we just calculate, then the objective function would be here, it would be half at this point. This is again half, this is again 1 and 1. Alright. Then, by looking at the values, you could see that 1 0 and minus 1 0 we are getting the maximum values, and half and here we are getting the minimum values. If we just go back to the figure, we could see that 0 1 by root 2 and 0 1 by root 2 we are getting the minimum value, and if the circle moves further and further, when it touches these two extreme points, then we are getting the maximum value. Alright. This is the thing we are getting from here. That is why we could see that there is only one constraint, and that constraint is active constraint. Now, I will show you more examples where I can show you that there are certain constraints which are not at all active. That is why up to this we have come across few new concepts. One thing is that the definition of the regular point, and we have to define it. What is the definition? If we are having m number of constraints, a point which satisfying all m constraint, that is the regular point of the constraint set. Not only that, at the regular point all the gradient of the constraint must be linearly independent. Alright. This is the definition. Not only it is in the feasible space for the nonlinear programming problem, but also there is another condition, gradient at the regular point. These are all independent. In other way, we can say that there is another property, that the Jacobian matrix of H x star is of full rank. What is the meaning of that? I will tell you. What is the Jacobian of H x star? Now, we know H is equal to H1, H2, Hm, there are m number of constraints, and this is of function x, H1, H2, Hm, these are all function x which belongs to Rn, alright. That is why m number of constraints, n number of variables. Now, if we consider the Jacobian of Hx, this is equal to grad of H1, x1, x2, xn, grad of H2, this is a vector, x1, x2, xn, up to grad of Hm, x1, x2, xn. This is the Jacobian. But why did we say that this is a matrix? That is a matrix because grad of H1, when we have x1, x2, xn, then this is equal to, we can write down the whole matrix as H1 del H1 x del x1 del H1 x del x2 del Hm, this is 2, no sorry 1, and the last term is del H1 divided by del Xm. The second row del H2 x del x1, this way we will go del H2 x xm. You must be understanding that we are getting a matrix, and what is the number of rows and number of columns you could get. Number of rows would be m and number of columns would be n. Now, it has been said that this must be of full rank. That means, always we should find out rank of Jacobian of Hx must be is equal to m. Okay? This is the condition. Jacobian of Hx is equal to m. Hmx divided by del xm, this is xm, xn. These are all n because there are n number of variables, these are not m, alright. Now, we need to find out that rank of Jacobian of Hx is equal to m. Not only that, we need to find out, if we consider, then what is the regular point then? Regular points are the points in Rn such that it satisfies the constraint set okay, and we need to find out that if this is a space, we need to find out if S is the space for it, because we will get different x here, combination of x will form a space. We need to find out that dimension of S is equal to, that is the number of variable minus number of constraints. That is why we need to prove two things here. One thing is that dimension of S is equal to n by m, and another thing is that rank of Jacobian of Hx must be is equal to m. Let us consider few examples for it. Both the examples we will consider one by one. The first example is that we are getting Hx is equal to, there is only one constraint, that Hx is equal to x2 minus x3 square. It has been said that x is in R3 only, alright. When we are dealing with the regular point, we are only dealing with the constraints. The constraint is not having x1, that is true, but objective function must be having that. And here we are considering here n is equal to 3, m is equal to 1, we have to find out dimension of S must be is equal to n minus m, that is equal to 1, alright. Now, if this is so, if we just find out the Jacobian of Hx, since only one, that is why our we will get a column vector. With respect to x1 it is 0, with respect to x2 it is 1, with respect to x3 it is minus 2 x3. This we are getting. Okay. Grad of h must be is equal, grad of h is this one. What you are getting from here? We are getting that, what is the dimension of this thing? Dimension of this thing would be 2. That is why we can say that S, that is the collection of all x which satisfy the constraint, it has only dimension 2. We can say the dimension of S is equal to n minus m is equal to 2. Now, the next example we have considered, here we are considering n is equal to 3, but m is equal to 2. We have two constraints together. Alright, one constraint is h1x is equal to x1 and h2x we have is equal to, this is x1, this is equal to x2 minus x3 square. Then from here we can get that grad of h1x is equal to 1 0 0, grad of h2 is equal to, what is that? 0 1 minus 2 x3. Alright. That is why from here what we can, first of all we have to say that this is the regular point. If we can say that grad of h1 and grad of h2, these are linearly independent, then only this is the regular point. Okay. That we can prove very easily from here, that both are linearly independent. One cannot be expressed in terms of the other one. Okay. You can very easily you can find it out. And not only that, from here we can say dimension of S is equal to, dimension of S is equal to that dimension. What is the dimension for this thing? Let me just explain to you. Now, say we are having 3 coordinate axis. Now, one function is x2 minus x3 square. How it looks like? This looks like this. Because this is a surface for us. Alright. Now, this is the surface. There is another constraint for you, x1 is equal to 0. We are having the, this is x axis, x1 axis, this is x2 axis and this is x3 axis, 3 dimension. This is your h2, this is your h1. If we just take h1 x equal to 0, what exactly you are getting? You are getting only one, this one, nothing else you are getting. In one dimension, x1 is just cutting here, because cross section, because this is a plane, x1 equal to 0 is a plane, the cross section of the plane, and this one will be only one dimension. That is why graphically also we can declare that dimension of S, that the collection of regular points which satisfies both the equations, the dimension must be 3 minus 2 is equal to 1. Alright. Now, this is all about the regular point. Now, we will move to the inequality constraints in the next class. Thank you very much.